Hi everyone, welcome back. This is a continuation on the study of fluid static, and for today we are going to learn about buoyancy. So by the end of this class, students should be able to understand the theoretical part of buoyancy and stability and to solve basic calculation on buoyancy and stability. For our particular study on buoyancy and stability, I will separate buoyancy and stability in a different video. Okay, what does it mean by buoyancy? It's actually a buoyant force, which is a resultant upward force exerted by a fluid on a stationary body immersed in it. So it doesn't matter whether the body is floating or completely submerged. The buoyant force or the upward force will always be there for the body. Okay, if you can see from the right side on the picture, it is assumed that the body is actually dropped inside a liquid, and this is the surface of the liquid. The top part of the body is receiving a pressure from the top with this equation here, where this is the density of the fluid, this is the gravitational effect, and x over here is the distance between the surface to the top part of the body, which is x. So now the height of the body is denoted as h. So the pressure at the bottom, because of the effect of depth, will have a different pressure, and the pressure should be higher than the top, where the pressure will be density of fluid times the gravitational acceleration with x over here, which is the same as the top, plus the height of the body itself. Okay, why does it important for us to add the h? Because the buoyant force is caused by the increase of pressure with depth in a fluid. So the depth or the height of the body plays a big role in our calculation. So when we have these two equations over here, so we can actually find out what is the force of buoyancy. So to get that, we have the bottom part or bottom pressure minus the top pressure and multiplied it by A. So where is the A for this particular picture? The A is this surface over here, which is the area of the surface, the top part of the body. Because our design is 2D, we cannot see the back part of it, but this is actually looks like this. So this should be the length and this should be the width. So if you are trying to find the area, it should be length times width. Okay, so if you have that, and if you put in the equation there, you can see that this x and this x can be cancelled out due to this minus sign. So at the end, the equation becomes this way, and the h times A over here will equal to the volume. So at the end, the equation of force of buoyancy is equal to the density of the fluid multiplied by the gravitational acceleration multiplied by the volume, and the unit for this should be Newton. Okay, before we go further on the calculation, there are three buoyancy conditions that may occur when you drop a body inside a liquid. The first part is called a floating body. So this condition happens when the density of the fluid is higher than the density of the object. So what happened? The whole body will float on the surface of the liquid. The second part is called suspended body. This condition is when we have the density of the fluid equals to the density of the object. It means the body is not at the surface and the body is not at the floor of the liquid. And the third condition is called a sinking body, where the density of the fluid is lower than density of the object. It means the body will sink to the floor of the liquid. So the buoyancy itself is very simple. The idea is very simple, and practically the calculation comes from the Archimedes principle, where in Archimedes principle, the buoyant force acting on the body immersed in the fluid is equal to the weight of the object. So buoyant force is equal to the weight of the fluid displaced by the body. So and it acts upward through the centroid of the displaced volume. So these wordings over here can be represented with this equation. Force of buoyancy is equal to the weight of the body. So if you have a body like this, and we assume this is the surface of the liquid, okay, the weight of the object will go downward like this, and the force of buoyancy will go outward like this. Okay, so in order for us to do the calculation, we have to give the definition of FB. So the definition is the density of fluid multiplied by the gravitational acceleration multiplied by V displacement. So what is V displacement? It's actually area times H displacement, and H displacement is here, which is the distance where the height of the body which is submerged inside the liquid. For this particular body, this part that I have over here is submerged inside the liquid. So this is your HD. For the weight of the object, the density is the same. So the density is, the density is for the object, 9.81 meter per second square, but with a different volume, which is area times H object. And H object is actually the total height of the body over here. So if you can see from this equation, when you bring it down here, we can see the G on both sides are the same. We can cancel out. The area for both sides are the same also, because we assume for this particular study for fluid mechanics, we assume the body at the top should be the same surface at the bottom. If the surface at the top is different area than the surface at the bottom, the area for these two sides cannot be cancelled out.